Hello everyone, and welcome to this webinar of Ansys Discovery. Today we will look at the features of Discovery, both generally, introduction, but then we will focus on a demo where I will show you how to set up a classical CFD problem of an air intake filter. So what can we do with Ansys Discovery? This is a multi-physics solver in one single user interface, where you can rapidly evaluate deformation and stress on component and assemblies with a structural solver, or with a modal analysis you can evaluate natural frequency and vibration characteristics. We can also do thermal, conjugate heat transfer, and fluid dynamic analysis, which I will show you today. Also, Ansys Discovery contains a topology optimizer to provide you with new design concepts based on given manufacturing constraints on stress. So how do we simulate this in Ansys Discovery? First to say is that Ansys Discovery is an important step for the digital transformation of company who want to make simulation available for everyone. You have a fast and easy geometry preparation mode, single user interface environment for solving all the physics, design exploration mode with a real-time interactive simulation, and design verification mode, where you access the trusted Ansys solvers when you can perform high fidelity simulations. So the geometry preparation mode, which is called model mode, this is the same window as you are doing the simulation, so you can easily create and edit geometry within the entire simulation workflow for evaluating rapid design iterations. For those of you who are familiar with the space claim environment, you will find the same tools for geometry cleanup, simplification, and volume extraction in this environment. And then you have in Explore mode, where you find a live physics simulation, where you instantly will see the results after changing the geometry or boundary conditions. You can rapidly evaluate design concepts based on performance, such as flow rate or flow uniformity or pressure drop. I need to say here that the live physics solver in Ansys Discovery is a GPU-based solver. So you need a dedicated NVIDIA GPU, Quadro or GeForce card recommended, with a minimum of 4 GB of RAM is required. Once you find a good design candidate after doing the design exploration, you can go to something called refine mode, where you do the high fidelity simulation. And this allows you to control the computational grid, the mesh, on a much more accurate level, and also doing some tuning settings of the simulation and convergence settings if you would like to, and also transfer to then fluent or mechanical solvers with just one click. So this concludes the first part of this presentation, and now we'll go into the second to look at how Ansys Discovery works. So in this demo, I will show you how to set up this simulation model, showing you the geometry preparation and the fluid volume extraction, We will do the simulation settings, defining the inflow and outflow conditions, and tracking some convergence by adding monitor points. And then at last we will do some post-processing of velocity vectors and pressure contour plots, etc. So let's get started. This is how the Ansys Discovery interface looks like. You get this first welcome screen, and the first you have some videos explaining the user interface with the model mode, explore mode, and refine mode overview. Then you have instructions here on how to navigate with the keyboard and mouse, just some tips and tricks here. Then you have this interactive tours, which is really good to get familiar with the user interface. So I would like to start with opening up this, hitting F1 or opening this question mark, this overlay help it's called. So this allows you to easily understand all the buttons in the software, to go between different parts here, and you get this explaining text. Also sometimes you get these videos also explaining what the feature does. But let us open up now this model. You can do it either from file here by browsing or opening up recent projects here. You have the possibility to open up all kinds of native formats here, as you see. But today we will use this discovery file format. So as you can see now, when the geometry is loaded, is that we have the model tree here at the upper left corner, and you can highlight these different parts of the model. The inlet of the air filter is here, and the outlet is here. And if you want to look at the interior of a model, you can select the parts and press and make selected body transparent like this to visualize the interior. Or you can also go into this cross-plane mode by hitting X and just select the plane you would like to look at. Then you have these little icons here showing up, giving you the possibility to move between this planar view, or if you want to move the grid like this, or if you would like to just add a plane or go back to the original view here, 3D view. So what we will do now is to extract the fluid domain from this. So one way to do that is by using this volume extraction for watertight geometries. But there's also other ways to do it. If you have leakages that you cannot handling by closure, you can do Boolean extraction. But now we will focus on this volume extraction tool, where I find it here under prepare and click volume extraction. And then I select the capping surfaces of the inlet and the capping surface at the outlet, and then I select some surface that's facing the internal fluid. So by previewing the inside faces of this, I can make sure that I have a watertight fluid or not. So now when I preview this, I should only have the internal surfaces selected, but now we see that all of them on the exterior also are selected. So we have a leakage somewhere, and I happen to find this leakage now, of course. It was found here, so I can just simply use these space claim functionalities, which is very convenient, just by pressing delete. I space claim or Ansys Discovery here now automatically understands that this hole should be removed. So let us try again this feature and capping the inlet and the outlet surfaces, and then selecting some face here. Previewing now the surfaces that should be facing the fluid seems to be correct. Also, if this heads-up display, which is called, if it gets in the way, we can move it around like this, so it's not in the way when we want to select the different parts of the geometry. But we all set now for generating the fluid domain, and as you saw now, we got this fluid domain generated, and you can also find it here in the model tree. So let's take a closer look at this fluid domain. We find now that we have some imperfections of the fluid here. I mean, sharp edges that we don't want to include in the simulation, and this small cavity. So by editing the original geometry, we can update this fluid domain afterwards. So I will show you that. So we just can just inverse visibility of this. So we're showing the solids, and then I'm going into this cross-section mode to find the cause of these sharp edges. And I found now here these rounds here. That was the reason for this. So let us remove them by selecting simply this surface and double click on it. Will make all the neighboring surfaces selected as well. So we just want to make sure that all of them are selected around here, and we can just press delete. And we can do the same for this surface, this round edge here that created the sharp edge. Double click will select also all of these, the surrounding surfaces here. Then we have this intake tube of the air filter that we would like to close this gap. So we can do that either by just some pull function of this surface, or we can just move this whole object. And we do that by going to the design tools here, choosing the alignment tool here, and then I'm selecting this surface of the intake tube and using this position here as a reference for it to be moved. So if we now go into this the 3D mode again and showing the fluid domain and going to the model tree and right click and updating volume as it was created, we find that we get rid of these sharp edges and that small cavity that was created. So now we are happy with the level of details that's included in this fluid domain. We just, what's left to do is to extract the filter domain here. So we must split this volume. So we can then just switch on, turn on the filter and do Boolean extraction, which is used with this combine tool. So I'm basically selecting the fluid volume, which is the target body to be cut in, and then you see this little saw here, so I'm using my tool body here with the filter. And after this you see that we get these three different objects here. So we can rename them to something more clear. So this is our filter. This is our outlet fluid. And this is our inlet fluid. Also, normally in CFD simulation, we would like to extend a little bit inlet and outlets. So we do that by just using this pull function, selecting the surface we would like to extend and drag it by specifying 100 millimeters, for example, or you can just drag it as much as you would like to. And we do the same thing for the outlet. So we are almost all set. Before we would like to start to define our simulation settings, there's just one thing left to do, and that is to select which of these geometries should be included in the simulation and not. And we do that by just right-clicking on these three here, these parts, and say that we would like to simulate on selection only. And in that way you see that the icon here to the very left here becomes red on these parts, and these parts are green. So now is a good time for saving our model before switching to the simulation settings. So we just go and save our model. So to define the simulation settings, we go now into the directly to the refine mode, which is supporting these porous domains in this version of Discovery. And as you see now, we have a bunch of new buttons here that we can access. The simulation tab here with all its options. And once again, if you don't know or if you need any help, you can easily understand everything by switching on this overlay help. So first we would like to define the inflow conditions here. So we're simply selecting the inlet surface, and then we have this black hex, it's called, and this big these tools here, which is called the halo, and this really allows you to access a lot of tools easily, and define if you would like to do a structural simulation, a fluid simulation, a topology optimization, or add monitor points, etc. So there's a lot of features in this. So now I'm just selecting this fluid analysis, and I'm defining an inflow condition of 0.1 kilograms per second. So I'm just pressing OK here. And you see that this physics tree shows up here with all the boundary conditions of the walls and the inlet and outlet. So we do the same by selecting the outlet surface, but now we switch that it should be an outlet, and we can specify then velocity, mass flow rate, or pressure. This model should be air because it's an air filter, so we can make sure here that we have air as the defined fluid. But you also have the possibility here to switch between air or a lot of other fluids here. So we are now ready to define our porous media of the filter, and we just do that by again selecting this filter and accessing the halo, but now we select porous here. We will use this bidirectional definition of the resistant coefficients, and best practice is to use a cross-flow coefficient to be a couple of orders of magnitude larger than the streamwise coefficient, because in this way we can force the flow to orient itself in the streamwise direction, which is really the purpose of this filter, to straighten out the flow. So we just accept here, and after this we can find a small error message here in the physics tree here, telling us to define the streamwise direction of this filter. So we do that by just selecting some geometrical line that is parallel to the flow, and thereby removing that error message. So we are all set. We could just have a look also at the mesh, which is possible to control here in the refine mode and the fidelity of the result. So you can control the mesh by using this slider down here. So improving the mesh to the right or decreasing the mesh quality to the left here for more rapid evaluations of design. If it's not very crucial with the result quality. You can also control everything here from the global and determine the mesh quality based on curvature and proximity, or leave it just as to the default settings. We can also do some local fidelity control of the mesh by pressing this button here and then just selecting the surfaces. So we would like to do this because we would like to have the interface between the fluid and the filter should be good or the same quality at least. So by selecting here the faces and setting the same size, we can get the same mesh resolution. Ensure that. So I'm setting here now the 5mm fidelity control here of the fluid domain, and I'm doing the same on the filter, selecting the surfaces here and assigning a value of 5mm. And then you see also that these mesh settings are shown up here in the physics tree. So all properties related to the simulation settings, boundary condition and mesh are located in this. But you also got the view of all the geometrical parts up here in this region. So we are almost set, but left to do is also to add some monitor points. So to add the monitor points, we use the halo again, but here selecting monitors, and then we just selecting the outlet surface, which we want to monitor the velocity on. So I'm selecting here the velocity and then average here, which is the average area averaged velocity on this plane. I'm pressing OK here, and we see that this feature shows up here, the monitor overview. So we have both the user-defined monitors together with the default ones. That are the max velocity in the domain and the pressure drop. So I'm selecting now the inlet surface here and would like to monitor the static pressure on this surface. And after pressing OK here, we see that these two windows shows up, and by clicking here on the details of this, we will be able to monitor the values of the the velocity and pressure here at the inlet and outlet at each iteration of the simulation. Last thing we would like to monitor for the, understanding the performance also on this air filter is to look at the flow uniformity downstream the porous phase surface. So if I'm just hiding the outlet fluid here and selecting the surface here downstream the filter, we can select instead the flow uniformity and press OK, and this shows up here. So now we have defined all our inlet conditions, outlet conditions, porous domain, and monitor points. And as you see, if you ever get unsure what boundary condition is connected to what surface, you can always hover above that setting and you will see it highlighted always in the geometry as a reminder. So we are ready to start this simulation. So as the simulation starts, you can see this simulation information display of Ansys Discovery and a green line that's showing the progress of the solver. After 50% here, you can start looking at the mesh because that means that the mesh generation is finished. And you can also see some other information here regarding the what kind of simulation we are doing. So here it says a steady state fluid flow analysis. So if we start to look at the mesh, we can make a cross section to just make sure that our settings were done fine. So we can see the fidelity adjustment settings here that we did before of 5 millimeters, which apparently refines the mesh here at the filter and the interface, and it's a little bit coarser here in the middle. Also we can find the inflation layers here, which we have three prism layers here now because of the slider we set here. So if we drag this to a higher level, we will get the more accurately resolved boundary layers at the walls. As you saw there, it was just a second ago, it was switching over to the streamline plot automatically, and it does that, the solver, when when it starts to iterate towards a solution. So we can actually already now start to do some post-processing of the results, looking at any of these vector plot or contour plot, isosurfaces, streamlines, and a lot of other good tools. Also we have this legend here where we can select the variable to plot in this streamline plot here. So you can select the static pressure or total pressure or velocity, and also change the range here. But most importantly, also we find here the convergence here of the velocity, average velocity at the outlet, and the static pressure at the inlet, which is converging now. So you can wait for this automatic convergence criteria to stop the simulation, or you can also just wait until it finished. So now we see it's complete, the solution, and we can open up now some of these other plots, pressing the vector graph. So by setting these vectors as constant size and looking at the ZY plane, we can get some understanding of the performance of the filter, and we can see that the flow is obviously straightened out here in this region compared to the inlet here, which is really the intention of this airbox. So imagine now that we would like to save this view, because we would like to have this for a later meeting. We can use this save scene, which we find here, save current scene, and then you can, if you're in another view and would like to go back to this, you have all the quantity that's plotted and the view saved. So let us switch on the streamline here, and we would like to save a scene for this, and also we would like to save a pressure contour plot. And we might also want to just save just a neutral view of this geometry for model description. So in this way, we now can switch between these views very easily, and use that for report generation, which we find here. Just create a report. This will save all of these scenes, including a summary of the boundary conditions and all the material used, together with these scenes pictures, and also a 3D picture here, 3D model of the air filter. So this actually concludes now this demo, and I hope you found this interesting. I'm ready now to answer any of your questions if you have during this live interaction. So thank you.